Okay, so I hope it is now visible to everyone. Uh, uh, Let me again welcome you. So sorry for the interruption. So today in this lecture, we are going to see the recurrent themes in linear algebra. Okay, so by which I mean that I'm going to see what all questions have come in the exam that have got repeated. That have got repeated. Okay, so that is one thing. So we have seen that in previous year, most often we have found that the same question are being asked time and again. Okay, so therefore this lecture is very important for you all. It will serve as a revision material for you all also. Okay, so the first concept that I want to discuss is the linear transformation. It is the linear transformation. See, let T be defined from a vector space U to V such that T alpha u1 plus beta u2 is equals to alpha tu1 plus beta tu2. So let's say T is a function which is defined from a vector space U to vector space V such that T of alpha u1 plus beta u2 is equals to alpha tu1 plus beta tu2, where alpha belongs to some element in field and beta is also an element of field, and u1 and u2 both belongs to U. If this is a map, this particular mapping is called as the linear transformation. This particular mapping is called as the linear transformation. Okay, so this particular mapping is called as the linear transformation. Now question arises that why am I teaching you this particular concept? So see, you'll find that this particular concept is an important concept for examination in general, and otherwise also you'll find that most often things that you're writing, even in quantum mechanics, like say the operator theory. So when we discuss operator theory, we know that the operators that we discuss in quantum mechanics are linear operators. Okay, so basically whether I say linear transformation or I say linear operator, they are one and the same thing. They are one and the same thing. So for example, let me give you an example and then probably you'll be able to understand this particular concept. Okay. Okay. So okay. So now say let's say I give you one question. I give you one question and now you are asked to see that whether it is a linear transformation or not. Let's say you are given a question. I'm giving you a question and then you are asked whether it is a linear transformation or not. So let's say I'm seeing T x1 comma x2 comma x3 is given by x1 plus x2 minus x3. You have this 2x1 minus x2 and then you have x2 plus 2x3. Now you are told whether this is a linear transformation or not. You are told that whether it is a linear transformation or not. So what one needs to see? One needs to check both of these properties, right? One needs to check both of these properties, and if both of these properties are clear, then we can say that the transformation is linear. Okay, so this is a linear transformation. Let's say I take two values. Let's say I take x1 comma x2 comma x3 and I add it with y1 comma y2 comma y3, and let's say I do a beta here, I write alpha here, and I try to find this value. So what I will get, I will simply get alpha x1 plus beta y1, okay, comma, then I will have alpha x2 plus beta y2, comma, alpha x3 plus beta y3. Right, this is what I'm going to get. If I do T of alpha, let's say this is x, this is y in r cube will be defined like y1, y2, y3, x in r cube will be defined this way. Now if you just this is your x1, this is your x2, this is your x3. So what you do, you just use this up. So x1 plus beta y1 plus alpha x2 plus beta y2 minus alpha x3 minus beta y3, then a comma, then you have 2 times alpha x1 plus 2 times beta y1 minus alpha x2 minus beta y2, then comma, alpha x2 plus beta y2, and then plus, I think this is plus only, so this is plus, and it says plus 2 x3. What is x3 here? Alpha x3 plus 2 times beta y3. Okay, this is what it is. Now if I use all these terms, all these things now, so what I'll do, I'll write t alpha x1 comma x2 comma x3, then plus beta y1 comma y2 comma y3. It is equals to what? It is equals to all these fellows. Okay, so what I'll do simply one thing. I'll take this these things, so I'll write this alpha outside. I'll write x1 plus x2 minus x3, this was first, this 1 2 3, then comma, I will say this is 2 x1 minus x2, comma, I will say this is x2 plus 2x3, and then I will write plus beta, and here I will write y1 plus y2 minus y3, comma, 2y1 minus y2, and then I will write y2 plus 2y3. So what has happened? This is, let's say, this vector x1 x2 x3, I'm saying it as x, and let's say this vector y1 y2 y3, I'm saying as y. So what am I getting? I'm getting t alpha x plus beta y is equals to alpha. What is this? If you remember, this is nothing but tx, and if you remember, this is nothing but ty. So clearly it satisfies the property for the linear transformation, and I'll say that T is a linear operator or linear transformation. Okay, this is one. Now having said this, now understand that let's say you have r square. Let's say you have r square. What would be the basis set for it? Means what are those two linearly independent vectors in which you can span the entire space? So clearly x-axis and y-axis. X-axis can be written as 1, 0, y-axis can be written as 0, 1. Similarly, what would be those linearly independent vectors in which r cube can be spanned? I'm not saying that these are unique ones, but these are the standard basis vectors. Okay, you may span your r square by 1, 1 and 1 minus 1 also, but let me just write the standard basis. So standard basis for spanning the entire r square would be 1, 0 and 0, 1. Okay, this is one thing. And the second thing, let's say what is r cube. If I say that r cube can be spanned by 1, 0, 0, 0, 1, 0 and 0, 0, 1, so these will be the basis. These will be the basis. And when I'm writing x first, then y, when I'm writing x first, then y, then z, I say that these bases are arranged in an order. So these bases are called as the ordered basis. Is that clear till now? I hope it is clear. Please let me know if there is an issue, so that now this is the final time that I'm teaching, so that everything gets revised also, and you get to do all the questions that have come in the examination. I mean, is that clear? Okay, so this is one thing. So ordered basis. Now what happens is, we want to associate a matrix. So another important concept is matrix of linear transformations. We want to associate a matrix. Okay, so we want to associate a matrix of linear transformation. And what it is. This is what brings to an important discussion. So let U and V, let's say U is a m-dimensional vector space. Okay, let's say U is an, let's say I take n-dimensional vector space, and let's say V is an m-dimensional vector space. Okay, and let us say the basis in which you can span U is E1, E2, E3 dash 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 En. I hope you know this E1, E2, E3. E1 would be 1, 0, 0. This is n. Okay, these are n elements. Okay, and in which bases in which V can be spanned is E1, E2, let's say F1, F2, F3 dash 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 Fn. Now you see, if I do a mapping from T U to V, and E1, E2, E3 are the ordered bases in ordered bases in U, and I want to see that where TE1, TE2, TE3. So you know all these things. That is, if I take the image of all these things, that is, if I take TE1, TE2, where it will be lying? They will be lying in V. Yes or no? They will be lying in V. That is a vector space V. You can say set V. And you know that the set V is spanned in terms of F1, F2, F3 and Fn. Okay, so let's say I'm saying that let me say that let's say this is, let's say, R cube. I'm saying this is R cube. So I can write all these values like TE1, TE2, TE3 in terms of linear combination of X, Y and Z. Right? Yes or no? I mean, please let me know that. Otherwise you will not be able to get what I'm trying to say. Is that clear till now? See, what I want to say, let us say that U is a vector space of dimension n, V be the vector space of dimension m. If E1, E2, E3, En are standard bases, ordered bases in U, F1, F2, F3, Fm are standard bases in V. If I'm mapping this E1, E2, E3, En, they will be TE1, TE2, TE3 dash 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 TEN. All these will be contained in V. V is spanned in this terms. So can I not write that TE1 would be equals to what? It will be equals to some A11 F1 is that clear? A12 F2 A13 F3 and dash dash dash. You'll have this A1N A1MFM. Is that clear or not clear? Please let me know. And I'll write TE2 is equal to some A21 F1 plus A22 F2 and dash 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 A2M FM, and then I will write TEN is equals to AN1 F1 plus AN2 F2 dash 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 ANM FM. Now this coefficient matrix that would be created. So here is a matrix which contains all these TEIs. There would be some matrix, coefficient matrix here, and then these are FIs are here, right? You have to take the transpose of this matrix. You have to take a transpose of this matrix, and this matrix is known by the name called as a matrix of linear transformation. Please remember, it is called as a matrix of linear transformation. And most often you'll find that even if you are not aware with difficult concepts, if you do this, you'll be able to do everything. So let us do one question which has been asked in GATE examination. Let us begin this lecture, that is the recurrent themes in linear algebra. So the first question that I'm going to take is from the GATE exam. It says that a linear transformation T is defined as T of x1, x2, x3, and it is equals to what? It is equals to x1 plus x2, and then you have this x2 minus x3. Okay, and it says that what is the transformation matrix? What is the transformation matrix? So this is your theme number 1. So theme number 1, please keep in mind, is the transformation matrix. Please keep in mind, this is transformation matrix. Okay, so let me do. Okay, so see what it says. It says that T x1 comma x2. So what I'll say is that this is a transformation from where to where? It is a transformation from R cube to R square. What are the standard basis vectors in R cube? So standard basis vectors in R cube are 1 0 0, 0 1 0 and 0 0 1. Okay, these are the standard bases in T. If I apply T here, if I apply T here, if I apply T here, what will happen? What will happen? What will happen? So I've written all these things in, like I've taken a transpose of it. So instead of writing column, I'm writing row. So what will happen? This will be 1 comma x2 minus x3 simply 0. What it would be? X1 plus x2. So this is 1. And what is x2 minus x3? This is again 1. And here it is. What is x1 plus x2? This is 0. And what is x2 minus x3? This is minus of 1. So if I want to write in the basis of R square, as I told you, f1, f2, f3 are the bases. So if I want to write all these things in R square, like if I want to write this thing in terms of R square, what I can write? I can write 1 times 1 comma 0 plus 0 times 0 comma 1. Then what I can do? I can write it as 1 times 1 comma 0 and 1 times 0 comma 1, right? And then I can write 0 times 1 comma 0 and minus 1 times 0 comma 1. Is that clear? Now I told you that like 1 comma 0 and 0 comma 1, what are these? These are f1 f2, right? This is f1 f2, all these things. So here would be a matrix in T, here would be a coefficient matrix. So what would be the coefficient matrix? So if I want to write the coefficient matrix, it would be 1 0 1 1 0 minus 1 and then these elements. Now I told you, in order to write the matrix of transformation, you have to take a transpose of it. You have to take a transpose of it. Is that clear? So what would be transpose? 1 1 0 and 0 1 minus 1. So this would be your what you can say. This would be your matrix of linear transformation. This is called as the matrix of linear transformation. So please keep in mind, this is one of the themes which has not been asked in the examination now for quite a while. This question was asked in 2006. So please keep in mind, it may be asked in your exam now. Okay, so please keep in mind this theme. Again, I'm repeating, the theme is transformation of linear transformation. In our Sarthak series, I have repeated this concept almost like 3 times, because once I actually got puzzled in some writing these things. But in the next lecture, which is the linear algebra 8, there is a clarification video where I have clarified the doubt which has been created, and the same question has been done. The same question, thing has been repeated. However, I have not done the question. So please keep in mind, this is an important concept which may be asked in your examination. Things are very simple. Just try to write using this thing, like whatever mapping has been given to you. Try to use that mapping over the standard basis, and please keep in mind, use ordered basis only. So one of the thing I'm writing, please use ordered basis, otherwise you will not get the right answer. Okay, this I have discussed in the lecture in detail, that if you are not taking ordered basis, then the matrix will not remain unique and your concept shall not be valid in that particular case. So please remember this concept. Okay, this is the first thing that I wanted to draw your attention to, because most often we see that in examination, okay, the questions are coming from either eigenvalues or eigenvectors. We think that way, but that is not the case. It may be asked this way also. Okay, so now I'll take another question. However, it is not asked in the terms of, you can say, it is not asked like transformation matrix, but it can be done using transformation matrix. So this question was asked for the JAM candidates. However, we are going to do this question without using something called as Jacobian. So if you remember, if you want to, let's say if I have a XY system and if I want to get into R theta system, so what do? I use something called as Jacobian matrix. I use something called as a Jacobian matrix. So if you remember that if you want to write dx dy, this does not go dr d theta. So there is something called as r dr d theta. And you think that why it is happening? So it is happening because of the Jacobian matrix. Okay, now what if you don't remember this? What if you don't remember this? So obviously what is happening? You are transforming from one coordinate system to another coordinate system. So you may associate a matrix of linear transformation here. You may associate a matrix of linear transformation here. And from here also you can do the question. Let us see how. So consider the transformation. So question was asked this way: consider the transformation to a new set of coordinates, that is zeta, eta, from rectangular coordinates xy, where zeta is given by 2x plus 3y and eta is given as 3x minus 2y. It says in the zeta comma eta coordinate system, the value of dy dx would be equals to what? So value of dx dy would be equals to what? So most often you will find that these questions can be done using the Jacobian matrix. However, I'm not going to use that particular matrix. Why? Because I have certain different ways also to do it. So let's say this is eta zeta eta, and this is related by this. So let's say this is 2 3 minus 2, and this is x and y, right? Is that clear? So always remember, if I want to take the area element, so what is area element in x and y? So if I use, instead of x and y, if I take the derivative, so this will be d zeta, d eta, this will be dx, and it would be dy. So what would be the area element? Differential area element would be dx dy, and differential area element here would be d zeta, d zeta and d eta. Obviously it would be, so what is happening? So this is, let's say this is t. So whenever you have this kind of question, always remember, if I want to write the area, what is the way ahead? Try to use this thing. Try to use this particular thing. Try to use this. So what will be the matrix of transformation? I told you it will be 2. So like it will be 2 3 and 3 minus 2. Is that clear or not clear? Okay, just take the determinant of it and take a modulus value. Take a determinant of it and take a modulus value. So what it would be? It would be 4, like minus 4, minus 9. So if I take a modulus value, it will be 13. It will be 13, right? So if I take if I take a modulus of it, just remember, I'm writing a formula. This is area in zeta and eta. This is area in zeta and eta is equals to 13, which is the determinant of this, and area in this, dx in dy. So answer would be that dx dy can be written as 1 upon 13 d zeta d eta, and things are done. All you need to do is just try to find the determinant of the matrix of linear transformation. Take the determinant, take a modulus value, because area can never be negative, and then you can relate things. So if I have done this way, so I just take a determinant here. So determinant would be 13 dx dy is d zeta dn. So 1 upon 13 d zeta dn would be dx dy, and things are done. So you don't need to get into Jacobian matrix. If you remember Jacobian matrix, then it's fine. If you remember Jacobian matrix, then it is fine. So if you don't know this way, and if I want you to know Jacobian matrix, here it is. So whenever you have to change from one coordinate system to another, let's say if I have dx dy, I use something called as a Jacobian matrix, and I'm going to write it in a way that you should remember this. This is Jacobian determinant I'm using. So I'm going to write the matrix also, don't worry. Okay. This particular thing is called as a Jacobian. Now it relates one coordinate system to another coordinate system. It relates one coordinate system to another coordinate system. Okay. Now what is, I'm going to write what is, and always remember dx comma y upon d zeta comma eta is equals to, if I write this way and this way, And why I'm doing this? Because I know zeta and eta in terms of x and y. I know zeta and eta in terms of x and y. So I'm going to find this, I'm going to find this, and then I'm going to write this way. So remember what it would be equals to. It would be equals to, I'm writing I'm writing determinant, and please take a magnitude also of it, because if you don't take a magnitude of it, then things may not work that way, because see, area is after all in positive sense only. So I'll write d theta upon dx, and then you have d eta upon dx. So this coordinate with respect to x derivative, and this coordinate with respect to y. You have to take this way. So what is this? Zeta was given as what? Zeta was given as 2x plus 3y. So if I take a derivative, so I'll get 2 here, I'll get 3 here, I'll get a 3 here, and I'll get a minus 2 here. So remember, minus 4 minus 9, that is again take a magnitude, so it will be 13. So clearly you can say that this would be 1 upon 13. So if you remember this, this would be 1 upon 13. So 1 upon 13 would be equals to what? It is dx dy, and then you have this d zeta and d eta. Okay, I did this question using the matrix of linear transformation. Please remember, if you don't want to do this way, you can do that way also. The way I told you, that is also absolutely correct. Don't worry about it. So if you want to relate to areas, okay, let's say I'll give you another question, and then you will be able to understand what I want to say. So for example, here area element in 1 is connected to area element in 2. So if I want to connect these two, I have to just multiply with the determinant of the linear transformation. So if I take the determinant of this, I'll be able to connect both of them. So basically this transformation matrix is nothing but this is Jacobian matrix itself. I hope it is clear till now. Anybody who's watching these lectures, please let me know if you are getting it or you're not getting it. Okay, so let me do another question so that we'll be able to get what I want to say. So this question has been asked for the maths people. Okay, so don't worry, this is not going to be asked in your exam. But let's say if at all it is being asked in your exam, then what happens? So it was asked in NBHM exam in mathematics. Okay, and it was said that for xy belongs to r square, there was a matrix that was defined. This is tx comma y, which is x plus y upon root 2, and you have this y minus x upon root 2. This is how your coordinates are defined. That is, this is a transformation from r square to r square only. And it says that if d is a unit disk means what? It says that x square plus y square equal to 1. What is the area? What is the area of TD? Okay, so how to do these type of questions? Again, I told you, first do one thing, just try to write the matrix of transformation. Just try to write the matrix of transformation. So let me see, I'll use the standard basis. First step is use the standard basis. So please remember, this is a matrix of linear transformation defined from r square to r square. So what would be the matrix of what would be the standard basis? It would be 1 comma 0 and 0 comma 1. Okay, now try to write what is 1 comma 0. So t of 1 comma 0 would be equals to what? T of 1 comma 0 would be equals to simply 1 upon root 2 comma 1, sorry, minus 1 upon root 2. Okay, and if I want to write it, I can write it as 1 upon root 2 1 comma 0, and then I can write it as 1 upon minus 1 upon root 2 0 comma 1. And similarly, if I write what is t 0 comma 1, it would be it would be 1 upon root 2 comma 1 upon root 2, right? And I can write it as 1 upon root 2 1 comma 0, and then 1 upon root 2 0 comma 1, right? So this is some matrix here, forget about it. This is a coefficient matrix. Please remember, this is a coefficient matrix, which is 1 upon root 2 minus 1 upon root 2 1 upon root 2, and then you have this 1 upon root 2, and you have this Now what you have to take, you take a transpose of it. So what would be the transpose? 1 upon root 2 minus 1 upon root 2, 1 upon root 2, and then 1 upon root 2. Okay, so this is your matrix of linear transformation. This is your matrix of linear transformation. You have something here, you have something here. This something area, let's say this is area, I'll write it as A2. This area is, let's say, A1. So this area A1 is nothing but the determinant of this matrix times A2. Okay, what is the determinant? 1 upon root 2, 1 upon root 2 is 1, minus minus, so it will be 1. Okay, and what is the area of A2? What is the area of, let's say, okay, what is area of, what is A2? Are you getting my point? So we want to find what is A1, right? We want to find what is A1. We want to find what is A1, right? This is what we want to find. And what is A2? A2 is uh, A2 is that particular area where your unit standard bases are 1, 0 and 0, 1, right? So here, so I can write it here. So I'll write it here. So what is these? These are the standard bases in D. Okay, and what are these? These are standard bases in TD. So if I want to relate area, so the area described by this would be equals to determinant of this into area described by this. What is area described by this? You know that in D you are talking about a unit radius, unit circle. And what is the area of unit circle? Pi into 1. So what would be A2? A2 would be simply pi into 1. What would be A1? A1 would be equals to 1 into pi. So answer would be simply pi. So this is how you do questions. Okay, this is how you do your question. Okay, so this is first concept that we have covered. Now let us cover another concept which is extremely important, which is eigenvalues and eigenvectors. Now here is the biggest deal. This is your theme number 2. So theme number 2 is simply eigenvalues and eigenvectors. So having done all these things, that is the linear transformation, a little bit about transformation matrix. Now this is theme 1. Why I have given it theme 1? Because see, this is the most basic theme. It has not been that exploited in the exam. Now it may be asked in the examination. So point number 1, theme number 1 was linear transformation. Theme number 2 is eigenvalues, eigenvectors. As you know, this is one of the most important theme in the examination. You'll find that each year, almost every year, they have asked questions from this particular topic, whether it is JEST, whether it is NET, whether it is GATE, whether it is JAM, whether it is any of the examination in India regards mathematics or physics. This is something that you can expect each year. Okay, and a little bit of you can say a little bit of even a little bit of understanding would help you do the questions also. Okay, so what we'll do, we'll start with a little bit basic, and then we'll see what all again themes are being asked in this particular topic. So I'll start with little bit basic, okay, so that you'll be able to get what I want to say. Okay, just give me a minute. I hope everybody is getting what I'm teaching right now. I don't know how many people are attending this lecture, but let's say, so I am saying that consider a linear mapping. Let's say consider, I'm just giving you an example. Consider a linear transformation or linear mapping, whatever suits you. Linear mapping from R square to R square. And let's say what happens is that you take this Tx comma y and you write it as 2x comma 2. So can I not write it as 2 times x comma y? Okay, so what is happening in such a situation? In such a situation, we say that 2 is an eigenvalue. We say 2 is an eigenvalue. So let's say if your map linear transformation is such that Tx comma y, so let's say Tx comma y is simply lambda x comma lambda y. So you just take lambda common out and you get x comma y. So clearly this lambda is called as the eigenvalue. Okay, so I'll write it here. an eigenvalue of a linear transformation T defined from V to V. So let's say there is a vector space V and we define a linear transformation from V to V. What is an eigenvalue? It is a scalar. Lambda belongs to field F such that what is happening? Such that there exists a non-zero vector x belongs to V such that if I do Tx, I get lambda x. So what I'm saying, that what is an eigenvalue? Eigenvalue is this lambda. So if I define a mapping from V to V such that Tx gives me lambda x, where x is a non-zero you can say non-zero vector, then this particular equation is called as the eigenvalue equation, and this particular lambda which belongs to field F is called as the eigenvalue. Please do remember, this is an important concept, supremely important. Okay, you'll find that each year in the exam this is a concept from various question, and this particular non-zero vector x is called as the corresponding eigenvector. This is called as corresponding eigenvector. I hope it is clear. I hope everybody knows this. Okay, is that clear? Now, how to extract the eigenvalues? Okay, so there is something called as characteristic polynomial. So there is something called as the characteristic polynomial. So how to extract the eigenvalues? This is another thing that you should keep in mind. So I'm going to write all these things because if not many people have attended the lecture, then they will get to know what I'm up to. Okay, so the point number 1, how to, just give me a minute, okay. Okay, how to find the eigenvalues. So if you remember that if I have this equation Ax is equal to lambda x, what I do, I find a characteristic polynomial corresponding to it, which is nothing, which is equals to, what is the characteristic polynomial? Characteristic polynomial to this particular thing, let's say I'm writing x here, so px would be nothing but it will be equals to determinant of a minus of lambda I. From here I get the values, different values, and these different values of lambda I are called as the eigenvalues. Let us say in this particular scenario, your eigenvalue lambda 1, when I factorize this particular polynomial, which is the characteristic polynomial, this is called as the characteristic polynomial. I'm writing it here. This is called as the characteristic polynomial. So if let's say this is getting repeated m1 times, this particular factor is getting repeated m2 times, and let us say x minus lambda n is getting repeated mn times. What are these called? These m1, m2, mn are called as the algebraic multiplicity. Please remember, name the algebraic multiplicity. So what is happening? I'll help you with some example also. Let us say I have some, I get a polynomial of this form. So what does it imply? It implies that x is equal to 2 is an eigenvalue with multiplicity 1, and x is equal to 3 is an eigenvalue with multiplicity 2. So this multiplicity is called as the algebraic multiplicity. Please remember, this is the first thing. Okay, yes or no? Please let me know in the comments, otherwise I'll not be able to get. Please let me know if all the people are getting the point. Just give me a minute. I think I'll have to start with the video also. Okay, so please let me know yes or no. Are you getting this point? Okay, So not many people are answering. So this is one thing. Another important concept that you should remember is that the product of eigenvalues, let's say you have a n cross n matrix. Let's say you have a n cross n matrix. So the sum of all the diagonal elements are called as the trace, and the determinant you know. So if I do a product of all the eigenvalues, what do I get? I get the determinant of this matrix. If I do a product of all the eigenvalues, I get the determinant of this matrix. And if I sum all these eigenvalues, what do I get? If I sum all these eigenvalues, then I get the trace of the matrix. Is that clear? Yes or no? Nobody is giving an answer. Please be responsive. Otherwise, I'll not be able to get whether you are getting it or not getting it. I mean, these are all easy things, but still. Okay, so this is one thing. So another thing that you should remember, so these are points I'm writing. The first point you remember the definition, the second point eigenvector, the third point I have stated this thing regarding this thing, and almost since you know that let's say you have a matrix A which is of n cross n, so corresponding to it the characteristic polynomial will be of degree n, and since it is of degree n, it will have at most n real solutions. It will have at most n real solutions, by which I mean if you have an n cross n matrix, then it can have at most n real eigenvalues. Okay, another important thing now with regards to something called as a triangular matrix. So if you have a triangular matrix, then always remember, what is a triangular matrix, by the way? So I'll write it formally so that you are not confused. So if you are given a triangular matrix, then always remember that the eigenvalues are nothing but the diagonal elements. The eigenvalues are nothing but the diagonal elements. Okay, so there are two kind of generally people get confused, so I'm going to write it so that you are not confused that way. So always remember that if this is a kind of matrix I'm writing, let's say there are this is the principal diagonal, and below it all the values are 0. If all the values are 0 below the principal diagonal and all the values are 0 above the principal diagonal, so such matrices are called as a triangular matrices. Such matrices are called as a triangular matrices. This is called as the upper triangular matrix, and this is called as the lower triangular matrix. Okay, if this is a kind of matrices we are talking about, the eigenvalues will be nothing but the diagonal entries only. And now let us come to different other systems for which we want to remember what all the eigenvalues are. So let's say I'm drawing a circle so that we'll be able to understand what I want to say. Okay, so let me draw with my hands only. So let's say I have a circle of unit radius. So I'm going to explain this particular thing itself. So let's say this is a circle of unit radius, and now I'm going to do something very important. I hope everybody knows Hermitian matrices, Q Hermitian. So this is something that I'm not going to teach because that I have taught already. So always remember, if a matrix is idempotent, then the eigenvalues are either 1 and 0. Okay, so if the matrix is idempotent, then the eigenvalues are either 0 and 1. If a matrix is nilpotent, then the eigenvalues are always 0. If the matrix is orthogonal or unitary, then the eigenvalues modulus is always 1. For what? Either they are orthogonal or they are unitary. Okay. If the matrix is Hermitian, then always remember that their eigenvalues will be real, whether it is symmetric or Hermitian. Okay, and if the matrix is skew Hermitian or skew symmetric, then the eigenvalues will be purely imaginary. So with these things in mind, now let us start with the questions. Okay, so remember, this is an important theme. Triangular matrix, sorry, eigenvalues, eigenvectors is an important theme, and so this is theme number 2, which we are discussing. Okay, so this is a really important theme. You'll find most often the questions have been asked from this particular theme. Okay, so let us do questions from recent years. Okay, and then I'll okay, so let us do one of the question that was asked in I think TIFR exam. So let us do from TIFR only first. Okay. Okay, the question says, this is TIFR, I think 2020, right? TIFR 2020. It says that the eigenvector E1 corresponding to the smallest eigenvalue, correspondence to the smallest eigenvalue of the matrix given by 2a square a0, and then you have a1 0, and then you have 0 0 sorry 0 a and 2a square. This is what has been given, where a is written as root over 3 upon 2 is what? This even was asked. This even was asked. So how to find it? Clearly, first we have to find the eigenvalue. So I have told you how to find eigenvalue. You have to find this 2a square minus lambda a 0, and then you have this a, you have 1 minus lambda, and then you have 0, sorry a, I think, sorry, and then you have this 0 a 2a square minus lambda. You have to take this determinant equal to 0, equate it to 0. So what you will get? You will get 2a square minus lambda, and then this is 2a square minus lambda times 1 minus of lambda minus of a square minus a, and then this would be a times 2a square minus lambda, and then simply you will have 0. So I'm not writing that, is equal to 0. Okay, now in this, from here you can know that 2a square minus lambda you can take common out, and inside you will have this 2a square minus 2a square lambda minus lambda plus lambda square minus a square, and if I take this particular 2a square minus lambda, so this minus a square would also come, so this is it. Now so this gets cancelled. You're going to have, if I take a negative, so I'll get lambda minus 2a square, and then I can take this, this would be lambda square minus of 2a square plus 1 lambda equal to 0. From here you know that one of the eigenvalue is 2a square, another eigenvalue is 2a square plus 1, another eigenvalue is 0. Clearly you know that if a belongs to R, you know that a square would be in any way greater than 0. However, the a here itself is given to you, so clearly this would be greater, this would be greater, the smallest eigenvalue would be 0. So this is the smallest eigenvalue. So this is the smallest eigenvalue. If this is the smallest eigenvalue, we want to find corresponding to this, we want to find the eigenvectors. In case of eigenvector, what we do, we take this and multiply it with the column vector. So I'll do one thing, 2a square minus lambda, lambda is 0, forget about it. So this is 0, this is 0. I think this was a, this is 1, and this is 0, and this is 0, and this is a, and this is 2a square. Why I'm not writing lambda? Lambda is 0. So now this is x1, x2, and this is x3, and then this is equal to what? This is equal to 0. So clearly this is equals to 2a square x1 plus a x2 equal to 0. The second one would tell you a x1 plus x2 plus, I think again this is a only, plus a x3 equal to 0. And the last one you will have this a x2 plus 2a square x3 equal to 0. You have three equations, 1, 2, and this is your third. What you do, you subtract 3 from 1. What you will get 2a square minus, 2a square x1 minus x3 equal to 0. So from here, x1 would be equals to what? X3. X1 would be simply equals to what? X3. And what would be x2? If x1 is equal to x3, I can say that my what would be my x2? X2 is simply minus of a x1 plus x3. So I can write that my x2 is nothing but minus 2a, and I know what is my a. My a is root over 3 by 2. So I'll write it as minus 2 root over 3 upon 2, which is nothing but minus of root over 6. So what would be my column vector E1? It would be equals to 1 minus of root over 6 and 1. If I normalize it, I will get 1 upon root over 1 square plus 6 plus 1 square, and then I have this 1 minus root over 6 and this 1 written all over here. Is that clear? And if I want to express it in terms of examination, so in examination it was given in row terms, so you will get 1 upon root 8, which is 1 upon 2 root 2, and you will have 1, 1 and minus root over 6 here. Okay. And in exam, 1 upon 2 was taken common, so I'll write 1 common out. So this is 1 upon root 2. It is in transpose. So if I take E1 transpose, then examination, the options were given in transpose. Don't worry. So answer would be 1 upon 2. This would be 1 upon root 2. This would be minus root over 3, and then 1 upon root 2. So this was the answer in the examination. So this is how you do questions in exam also. So you'll find that with a calm head, if you want to do all the questions, you're going to get all the questions you're going to get if you're doing it with calm head. And if you're doing it like haphazard, then you'll not be able to get the answer. In fact, you're going to get confused in the exam. So please keep your mind very chilled out when you're doing all these questions. These are not difficult questions. Please remember, these are not at all difficult questions. Okay, is that clear? Please let me know if this is okay. So now let us do another question which was asked in JEST exam, latest exam. I think that was asked in JEST exam. Okay, so question says calculate the largest eigenvalue. So this is a little bit tricky one. I mean, it will take time, but it's an overall it will take time, but it's not that difficult also. So this was asked in latest attempt, JEST 2023. Okay, and it was asked that it was given you were given a matrix of this form: 1, 1, 1, 2 and 3. This is, I mean, they are apart, don't worry. So this is 12, this is 2, 3, 2, 1. Then it was given 0, 0, 0, 2, 2. It was given 0, 0, 3, 0, 3. And then you will have this 0, 0, 0, 0, 1. Now it was asked, what is the largest eigenvalue of this matrix? What is the largest eigenvalue of this matrix? Obviously, this is a very tedious question. I mean, tedious as in you'll have to do it. You'll have to do it. You'll have to calculate. Plus, do remember why only, like, why people are interested in finding the largest eigenvalue. What is so crazy about it? So basically, remember these values are called as, in technical term, called as a dominant eigenvalue. And if you pursue something like quantum information computation, network theory, complex systems, you'll find the physical interpretations corresponding to the dominant eigenvalue and the eigenvector corresponding to it. So these are very important eigenvalues as such. So they have some physical context with regards to the specific field you are working in. Okay. So so this is a big one. What you're going to do, just be clever, try to expand your matrix from here, because you see there are 4 zeros here, otherwise this will become a mess, so you just try to expand things from here, and then you will be able to get the correct answer. So I have done it for you, so I'll do it directly. So 1 minus lambda, it was given here, it is 1, 1, 2 and 3, and you had this 12, you had this 2 minus lambda, 3, 2, 1. I'm going to just demonstrate the steps, because this is something that I've done already for you, because I thought that if I'll do it live, then even if I make a single mistake, then it is over. So try to expand from here. Try to expand your determinant from here. Okay, try to expand your determinant from here. So if you expand it from here, you will get 1 minus of lambda, and then you have this entire thing, 1 minus lambda, 1, 1, 2, and then you have this 12, 2 minus lambda, you have 3, 2, then you have 0, 0 minus lambda 2, and then you have 0, 0, 3 and minus lambda. Okay. Now, one thing is very much clear, that this is done. Lambda is equal to 1 is one of the eigenvalues. Now, what remains to be seen this. Now, what you do, again expand from the last row. Okay. So now if you do that, what you will get this minus lambda. I'm just writing it here. You just confirm what on your own. So this is 1 minus lambda, 1, 1. And this is 12, this is 2 minus lambda, 3, and 0, 0 minus lambda, and then minus of 3, because okay, so the minus of 3, and then you will have 1 minus lambda, 1, 2, and then you have 12. You please confirm it on your own, okay? Otherwise, okay. Now if you solve this particular equation, you will get something like this: lambda square minus 6 times 1 minus lambda into 2 minus lambda minus 12 equal to 0. And if you solve this, you will get lambda is equal to plus minus root over 6. This is 1. And from here you will get 2 plus lambda square. So up till this I have solved, because otherwise it will become such a big question to be solved. So lambda square minus 3 lambda, and then minus 12 equal to 0. So from here you get lambda square minus 3 lambda minus 10 equal to 0. So from here you can clearly see this is lambda square minus 5 lambda plus 2 lambda minus 10 equal to 0. So other two eigenvalues would be minus 2 lambda is equal to plus 5 plus minus root 6, and then lambda is equal to 1. 1, 2, 3, 4, 5. So in totality you have 5 eigenvalues. The highest eigenvalue would be lambda is equal to 5. So largest eigenvalue is 5. Largest eigenvalue is 5. So this is one of the zones from where you will find that each year, almost each year, the questions are being asked. So this is theme number 2, which is eigenvalues and eigenvectors. Okay, so a few more questions I'm going to give you. Okay, so that you are able to do them. Achha, again, one of the more important theme is, this is again one of the most like you can say repeated kind of theme. This is matrix with all entries 1. So this is, you can say theme number. Let us say that I'm talking of, it's working. Okay, so let's just give me a minute. I think there is a battery issue. Okay, so just give me a minute. I'm giving you a straightforward result. You'll always have 1 as eigenvalue, and this 1 as an eigenvalue will be repeated n minus 1 times. So in physics terms, you can say that the degeneracy of this eigenvalue would be 1. Degeneracy of this eigenvalue 1 would be, sorry, n minus 1. Okay, and the other eigenvalue would be the trace of the matrix. Sorry, one of the eigenvalues would be 0. Okay, one of the eigenvalues would be 0, and it would be repeated n minus 1 times. It would be repeated n minus 1 times. Is that clear? The first thing is clear. And the other eigenvalue would be simply the trace of the matrix. So always remember, if you have all the entries 1, if you have all the entries 1, if you have all these entries as simply 1, then always remember that the eigenvalues would be 0 with degeneracy n minus 1, and the other eigenvalue would be simply trace of the matrix. The other eigenvalue would be simply trace of the matrix. Please remember, this particular concept has been asked in JEST exam of 2012. Okay, the same question you will find it was asked in NET exam of June 2012 or 2011 also. So it was given that you were given matrix 1 1 1 1 1 1 1 1 1, and you were asked the eigenvalues for the same. You were asked the eigenvalues. So from the above concept, you know that there would be 3 eigenvalues. The eigenvalue 0 would be repeated n minus 1 times, means this is 3 cross 3. So it will be repeated 2 times. And the other eigenvalue would be simply trace of the matrix, which is 3. The same concept again in June 2012 you will see being asked. With a little bit of twist, you can say that the same question. It is what should I say? It has been the same question which has been asked time and again. But you should remember that. Okay, what should I say? So it's not that way. Okay, so this is one thing. If it was not June 2012, I think it was the latest year. So remember, this is first of the concepts that I wanted your attention. Please remember, if all the eigenvalues are 1, I'm again repeating, if all the eigenvalues are 1, okay, if all the eigenvalues are 1, then always remember, if all the entries are 1, then always remember the eigenvalue 0 would be one of the eigenvalues, and it would be repeated n minus 1 times. It would be repeated n minus 1 times. And the other eigenvalue would be simply trace of that particular matrix. The other eigenvalue would be simply the trace of the particular matrix. Okay, so I hope till now everybody is getting the point. Please let me know if there is a doubt or difficulty that you're facing. Okay, so always remember this is one of the concept that has been asked time and again. I'm just giving you one more question. I think I know that question has been asked. Just give me a minute. Just give me a minute, okay? I don't know which year it was asked. It was an easy question again. So remember this as a concept. Please remember this as a concept. This has been asked time and again. Okay. So this is theme number one. Theme number two. Please remember this is an again important theme. It is matrix exponential. This is matrix exponential. So this is theme number 1.2. So if I'm saying that it's theme number 2.2. Okay, so first theme, if you remember, I taught you the linear transformation. The second theme I'm talking about is the eigenvalues, eigenvectors. In that particular theme, I'm talking about theme 2.1, which is the matrix with all the entries 1. Please remember, if there is a matrix with all the entries 1, then 0 would be an eigenvalue which will have degeneracy of which will have a degeneracy of n minus 1, and the other eigenvalue would be simply the trace. And now one more concept, which is matrix exponential. This has been very well exploited concept. Time and again people have asked the questions from here, and you'll find that almost every year the questions are being asked from here. So the question is matrix, the topic is matrix exponential. Just give me a minute, I'll write it. Okay, so if this is your matrix exponential, so matrix exponential is nothing but it is equals to, if I write e की power of a, it is equals to identity plus a square upon 2 factorial plus a cube upon 3 factorial, so on and so forth. In general, if I write e की power a, it is equal to summation k equal to 0 to let's say infinite, and then you will have this a की power of k divided by k factorial. Okay, this is called as your matrix exponential. This is called as your matrix exponential. This is first thing that you should remember. And let's say if your A is a diagonal matrix, if A happens to be a diagonal matrix, then what will happen? In the diagonal matrix, all the entries come in the diagonal. And they correspond to, if it can be diagonalized, they correspond to nothing but the eigenvalues. Then e की power A would be nothing but e की power lambda 1, e की power lambda 2 dash 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 e raised to power lambda. Okay, is that clear? This is one of the concept that has been time and again. This has been asked time and again. See, the first question that I'm writing it for you is NET exam 2011. Okay, this is NET 2011. It was asked that if M is given to you as 1, 1, 1, 1, 1, 1, and again 1, 1, 1, as it is given, it was told what is e की power m. What is e की power m? It was asked what is e की power m. So if you see, if I do one thing, if I just take, if I want to write e की power m, so I'll have to take the various power of m. So what would be m square? If you find m square would be simply 3, 3, 3. This I'm leaving it for you. You just, do it on your own. So if you do m square, you'll find 3, 3, 3, all rows 3. So I can write it as equals to 3 times m. If you try to write what is m cube, and you will find that your m cube is nothing but it is equals to 3 m square, and I can write it as 9m, or you can say it is 3, sorry, if I take m both sides, so this is 3m square, and what is m square? It is 3m, so it is 9m, or you can say 3 square. So similarly, if I want to write it in this fashion, what would be e की power m? E की power m would be identity plus m square upon 2 factorial plus m cube upon 3 factorial, so on and so forth. And I will write it as identity m, and what is m square? M square is 3m divided by 2 factorial. What is m cube? It is 3 square upon m divided by 3 factorial, so on and so forth. If I take identity here, and if I take m upon 3 common out, what I'll get? I'll get 3 plus 3 square upon 2 factorial plus 3 cube upon 3 factorial, so on and so forth. If you remember, what is this resembling to? See, e की power 3 would be equals to what? E की power 3 would be equals to what? It would be equals to simply okay, so I'll write e की power 3 as 1. Sorry, what is e की power x? E की power x is 1 plus x square upon 2 factorial plus x cube upon 3 factorial. If I write what is e की power 3, this is 1 plus 3 square upon 2 factorial plus 3 cube upon 3 factorial, so on and so forth. So this is equals to what? I'll write it as this way. So e की power m would be equals to identity plus m upon 3, and this would be e cube minus 1. So this is what is repetitively asked in the examination. You'll find that this is your theme number 2. What I've written, theme number 2.2. That is a matrix exponential. Now, if you see, there is one more thing that in this particular context that has been asked time and again, which is what is the determinant of e raised to power m? So it has been asked what has been the determinant of e raised to power a. So let's say I'm given a matrix. So I'll give you a question also, and you'll be able to understand what I want to say. Okay, so if you are given a question, let's say this one. So this particular question has been asked in NET exam only, and then there was a question in TIFR exam also. If I remember correctly, there are 2 questions. So always remember, if I want to find the determinant of e की power a, it happens to be e की power of trace of a. It happens to be e की power of trace of a. Please remember this one more. So what is the theme? Please remember the theme we are discussing is matrix exponential. One of the things is utilize this thing. I'm going to do a few more questions here. Determinant of e की power a is e की power of trace a. It is e की power of trace a. And if I have to do a question on it, so I'll do a question that was asked in NET examination. So question that was asked was, one of the eigenvalue of matrix e की power a is e की power small a. Here a is given as a 0 0 0 0 a, and you have 0 a and 0. And now it is asked the product of the other 2 eigenvalues. Product of the other 2 eigenvalues. The product of other 2 eigenvalues. So clearly I told you that if I have to find this, see what I'll do. I know that the product of eigenvalues, so here it is a 3 cross 3 matrix, so I'll write, so product of eigenvalues is nothing but it is equal to determinant of a. And instead, if I'm saying e की power a, so I'll say let us say that the eigenvalues product is simply defined by this, and it will be equals to what? E की power a into, let's say, eigenvalue some and another eigenvalue. So this represents what? This represents the product of eigenvalues other than e की power a. This is product of eigenvalues other than e power a. What is product of eigenvalue? It is equal to determinant of e power a. And what will be determinant of e power a? It will be e power of trace a. What is e power of trace a? It is simply e power a. So you can say that the product of other eigenvalues would be simply unity. It will be simply unity. Okay, if you compare both of them, you know that product is e power a into this is equal to e power a. So you know that this e power a gets cancelled. So your product of other two eigenvalue would be simply 1. Is that clear or not clear? Okay, so this is one of the important concept that has been asked time and again. Time and again you'll find this concept has been asked. So this was asked in NET exam. The same question you will find in TIFR exam, almost same. And it was asked again in 2018 itself. The question was, given a 2 cross 2 matrix, a 2 cross 2 matrix was given to you. It was 1 minus root 2, 1 minus iota upon root 2, and you had this 1 plus iota upon root 2, and you had 0. Let's say this is your matrix M. It was asked what is the determinant of e की power m. It was asked what is the determinant of e की power of m. What is the determinant of e की power of m? So clearly, if I use this, and see this particular matrix is diagonalizable by the way. So this particular matrix is diagonalizable. Okay, why? Because if you take, so okay, diagonalizability I have not discussed. Okay, I'll discuss it sometime in the later event. So if I take the M like conjugate transpose, what I'm going to get? One. So clearly this is a Hermitian matrix. And if matrix is Hermitian, then it can be reduced to a diagonal form. So I can reduce it to diagonal form. And if I take e की power something, so I'll get e की power lambda 1, e की power lambda 2, 0, 0. If I want to take the determinant of this matrix, the determinant would be e की power lambda 1 into e की power lambda 2. That is the product of eigenvalues. Okay, so let's say this is your matrix M. It can be reduced to a diagonal form. This is matrix e की power m. If I want to take the determinant of e की power m, so determinant of e की power m would be simply e raised to power lambda 1 plus lambda 2, which is e raised to power trace m. So if I want to do this, what will be the answer for this? Simply e raised to power 1. So trace of m is what? 1. Since trace of m is simply 1, so this will be e की power 1. I hope it is clear till now. Almost similar question you will find. I think this was asked in JEST also this year. Okay, similar question, exactly similar question almost. You will find that it was asked in JEST exam also. Just give me a minute. Okay, I'll find that question and write it for you, don't worry. So the question was, okay, I don't know where it has gone. Okay, so mostly you will find that these kind of questions are going to come in the examination. Time and again, you'll find that these questions are being repeated. Okay, so if I have written it somewhere, so I'll give you that question also. Okay. Okay, so this was a question that was asked in 2021, JEST. And it was given, the matrix was given this way. Okay, so matrix A was given by this 1, 0, 0, 1, 0, minus 2, 0, 0. And then you have 0, 0, minus 3, 0, 1, 0, 0, 4. Clearly, this matrix is a symmetric matrix. And I'll show later on that symmetric matrices are diagonalizable. So I can diagonalize it, and I can diagonalize it to write this way. And if I want to take exponential, then this would be equals to e की power lambda 1, e की power lambda 2, e की power lambda 3, e की power lambda 4. And if I want to take the determinant of this, so determinant of e की power a is nothing but the product of these eigenvalues. And if I take the product of these eigenvalues, remember it will be equals to e की power trace of a. So remember, since this particular matrix is diagonalizable, I can write that determinant of e की power a would be simply e की power of trace of a. And if I do the same, what I'll get e की power 4 minus 3 minus 2 plus 1, which is simply equals to what? Which is simply equals to e की power 0. Answer would be 1. So the same concept is being repeated time and again. See, it has been asked in the NET exam. It has been asked in the TIFR exam. Again, it has been asked in the JEST exam. So please focus on these points. See, matrix exponential, again they're asking. See, again, one more question I'm going to give you. And that is one of the fundamental concepts also in linear algebra. So that way you will be able to understand. Just give me a minute. I'll write it for you. Okay, so so one of the questions they are asking time and again is again this is again one of the recurrent themes I'm going to write. It is in, so if you remember, we are doing right now matrix exponential, and in matrix exponential we have done the concept number 1. We have seen how to manipulate with these things. Uh, the second thing we have seen, just give me a minute. Okay, so another thing that we have seen is this particular formula. Please remember this particular formula. The another concept that has been asked in TIFR exam. Okay, so so this is something that is very favorite for TIFR examination. So remember that this is something that was asked in TIFR 2017. And see, it says that a unitary matrix can be expanded in terms of a Hermitian matrix. So I'm not writing the entire question. Can be expanded in terms of Hermitian matrix such that u is equals to exponential of iota pi h upon 2. So this is what they have given to you. So what they have given to you is they have written that your unitary matrix can be written in terms of Hermitian matrix, which indeed is one of the theorems also. I'm going to discuss it in detail in linear algebra. But right now just pay focus on this particular question. So it says that a unitary matrix can be written in terms of a Hermitian matrix, and u is given by e की power iota pi h by 2, right? Now it says that if we know that u is equals to what? If we know that u is equals to 1 upon 2, 0, root over 3 upon 2, 0, 1 and 0, and you have this root over 3 upon 2, you have 0 and minus 1 upon 2, then u must be. So this has been asked in TIFR 2000 what question? 17, right? So just give me a minute. I'll show you why they are repeating this again and again. See, you will see the same question being asked again. So just give me a minute. Okay, I think this was asked again in TIFR, some very recent year. I remember. Just give me a minute. I'll give you the question also. Okay, so let us first do this question, TFR 2017. This question again represents an exponential of matrix. And what is good about this matrix? Please remember, if I am given a matrix, let's say this particular matrix has been given to me. Okay, this particular matrix has been given to me, and what to do? So what I'll do, I will simply try to I'll simply try to do a Cayley-Hamilton theorem here. I'll simply try to do a Cayley-Hamilton theorem. That is, I will find the characteristic polynomial here. I'll try to find the characteristic polynomial here. So this was asked in TIFR. And similar question, you'll find the similar question was asked again in TIFR itself. So I'll give that question also. So how to go about this question? So see, I'll first find the determinant u minus lambda I. And if you remember, this is unitary matrix. And for unitary matrix, the eigenvalues, the modulus of eigenvalues is always 1. The modulus of eigenvalues is always 1. Remember. This will do and try to place it equal to 0. If I do this thing, what I'm going to get? I'm going to get 1 by 2 minus lambda and then 1 by 2 plus lambda. Okay. This is fine. And again 1 minus lambda as well. With a negative sign. With a negative sign. See this. Okay, minus 0, forget about it. Plus root 3 by 2 and minus root 3 by 2, 1 minus lambda is equal to 0. This is one thing. See, and from here, if you take a negative and here take a negative common out, you are going to get 1 upon 4 minus lambda square, and then you have 1 minus lambda here, plus minus minus common, you have this 3 upon 4, 1 minus lambda equal to 0. So if I take a common, so I'll get 1 minus lambda into 1 minus of lambda square equal to 0. So according to the Cayley-Hamilton theorem, remember the characteristic polynomial is satisfied by the matrix itself. So if I do that way, so I know that h square would be equals to identity. Sorry, my h square okay, this was not u, this was h, my mistake. Okay, so h. So according to Cayley's theorem, the matrix would the matrix would satisfy the characteristic polynomial. So if it does so, my h square would be identity. If I use this, okay. Is that clear? This is first thing. And if I use this h square equals to identity, what I'm going to get, I'm going to write u is equal to exponential of iota pi h upon 2, and this will be equals to identity plus iota pi h upon 2 plus 1 upon 2 factorial iota pi h upon 2 ka whole square. Okay, then you will have plus 1 upon 3 factorial, you will have iota pi h upon 2 whole cube plus 1 upon 4 factorial iota pi h upon 2 whole power 4. Okay, now from here you will get iota plus iota uh, pi upon 2h. Okay, okay, then plus you'll have 1 upon 2 factorial, and then this is minus of pi square h square upon 2, and then you have plus minus, sorry, minus 1 upon 3 iota. So because iota cube is minus iota, you'll have pi cube h cube upon 8, and then you will have 1 upon 4 factorial. Iota power 4 is 1, this will be pi power 4, this will be h power 4, and this will be 16. So if I just arrange the terms, so u would be equals what? Identity plus, if I take this term, this will be minus of pi upon 2 whole square, minus of pi upon 2 whole square into 1 upon 2 factorial. Remember this h square is what? H square is identity. So I'll write identity here. Remember h ki power 4 would be what? H ki power 4 would be identity square. Again identity. So I'll write 1 upon 4 factorial pi upon 2 raised to power 4. Here identity, and so on and so forth. And then you'll have this term. So I'll have this. I'll take iota common. I'll write. I'll simply write iota h common, and then this is pi upon 2 minus 1 upon 3 factorial. This is h whole cube. And if you just think what is this, so I'll write this would be pi upon 2 h whole cube, right? And remember, what would be h cube? So if h square is identity, your h cube would be simply h. So what I can take h common. I can take h common, right? Now just think about this particular expansion. Don't you think this is, if I take identity common, isn't it equals to cos of pi by 2? And if I take iota h common out from here, isn't it equals to sine pi by 2? So what I am going to get, I'm going to get u is equals to simply iota h. Why? Because cos pi by 2 is 0. Forget about it, you will get iota h. And what was your h matrix? Your h matrix was given by 1 upon 2, 0, root 3 upon 2, 0, 1 minus 1, and then you had this 0, and again you had this root over 3 upon 2, 0, and minus 1 upon 2. So what would be your u? U matrix would be simply iota h, which reduces it to iota upon 2, 0, iota root 3 upon 2, 0, iota 0, and then you will have this iota root 3 upon 2, 0, and minus iota upon 2. So this is your unitary matrix U which we are talking about. This is the unitary matrix U that we are talking about. I hope it is clear till now. Okay, so this is one of the themes that they have been asking time and again. So please keep a great focus on all these concepts. I'm going to give you one more question. Just wait for a minute. Okay, so this was diagonalization. Diagonalization I've not taught you, so I'm not going to give you. Okay, so okay, just give me a minute. So question was asked in 21 also. Okay, so again a question was asked in 2021, and I'm going to write it for you. So again TFR 2021. So they've asked again that a unitary matrix is represented in terms of a Hermitian matrix. Okay, and which is given by u is equal to e की power iota pi h upon 2. And if the matrix is given by h is equals to root over 3, and then it is given 1 upon 3 0 root over 2 upon 3 0 1 upon root 3, and then you have the 0 root over 2 upon 3 0 and minus 1 upon 3, then u will be what? Again, try to do this question. Almost similar question. You will see that almost similar question they're asking. So all these things are freebies, because if you are practicing previous year question, then you will be able to understand that if they're repeating it, why should we not practice it? Why should we not practice it? Because if you practice it, then it will be these are easier question for your exam, right? So how to go about it? Again, the same concept, same way. What you're going to do, you're going to first find the characteristic polynomial. So what would be characteristic polynomial? It would be 1 upon root 3 minus of lambda. Then you will have 0. You have root over 2 upon 3. Then you have 0, and you have 1 upon root 3 minus of lambda 0. And then you have this root over 2 upon 3 0, and then minus of 1 upon root 3 minus of lambda. Right, the question is this only, no? I don't make, if I make a mistake, then I'll be gone. Just let me wait for a minute. Question 2, written, this question. Okay, this was how it was written. So this is 1 upon root 3, 1 upon root 3 means 1 here. Okay, if I multiply root 3 here. So this is one thing. If I take this determinant equal to 0, what I'll get? I will simply get this. So lambda minus 1, and then 1 minus lambda square equal to 0. Remember, this is the characteristic polynomial. One of if I say that this satisfies this, it implies what? It implies h square minus identity. H square should be identity. This is sometimes referred to as minimal polynomial. Please remember. What is minimal polynomial? Minimal polynomial is a polynomial of degree less than the characteristic polynomial, which annihilates this. So here, from here, you can know that this h square is equal to identity. Okay, because every matrix satisfies its characteristic polynomial. So instead of lambda, I can place h. So h square is equal to identity. This is the minimal polynomial. This is referred to as minimal polynomial, not characteristic polynomial. So characteristic polynomial is one that I have given you. This is called as a characteristic polynomial complete if a polynomial lesser degree than the characteristic polynomial satisfies the equation. That is, it satisfies it. So if you want to see, you can see this on your own also. If you try to do an h square from here, you will be able to find that. So it is satisfying, right? H is not equal to identity. Obviously, H is not equal to it. So if I do this, clearly H is not equal to identity. So it implies what? It implies h square should be I. This is referred to as one of the special names is given to is minimal polynomial. Okay. So what is a characteristic polynomial? Characteristic polynomial is this complete thing. What is minimal polynomial? Minimal polynomial is one of degree less than the characteristic polynomial and which satisfies like matrix which annihilates the matrix. If you do this h square, you will get identity, because you know that by characteristic polynomial, you know what? Every matrix, I'm writing it Cayley-Hamilton theorem, every matrix satisfies characteristic polynomial, isn't it? This is something that you know. And if it satisfies the characteristic polynomial, h cannot be identity. So obviously h square has to be identity. If h square is identity, then you know that your h cube would be simply h, your h power 4 would be again identity, and so on and so forth. So on and so forth. So if you just do this particular question, what you'll find, you want to find e ki power iota pi h by 2, and again the same concept being repeated, e ki power iota pi h upon 2, it would be equals to simply iota h. The same calculations that you did in the above question, they will be valid here itself, here also. So if it is that the case, then you'll find answer would be iota upon root 3, you'll have 0, then iota root over 2 upon 3, and then you have this 0, and then you'll have iota here 0, then you have root over 2 upon 3 iota 0, and minus of 1 upon root 3 iota. So this is an answer for your question. So remember, certain manipulations with regards to exponential matrix has been exploited time and again. You see the questions time and again, you'll find the questions being asked in matrix exponential. So one of the concepts that you need to remember is of the eigenvalue. So we are discussing what? Again, I'm just letting you know what is the theme of the topic. So the recurrent theme is that this is the first lecture in this series. We'll have only 2 lectures, probably tomorrow will be the last one. So recurrent themes in linear algebra. The point number 1 we discussed was linear transformation. Point number 2 we discussed was eigenvalues and eigenvectors. A little bit of brief outlook I have given to you with regards to the eigenvalues of all the special matrices. Then I have discussed with you the way how to calculate the eigenvalues, because this is time and again being asked, so I'm not much bothered there. Dominant eigenvalue, which was asked in JEST exam recent year. Matrix with all entries 1. Please remember, this is time and again being asked. So please remember, this is as a one of the concept that you can really vouch on. So basically, it will be asked. You can take that way. So at times they may create a certain deception with regards to this question, but more often you'll find that these questions are asked. So just give me a minute, I'll give you that question also. Okay, meanwhile, also remember that one of the important question is this also. So one of the important concept is matrix exponential, which I have discussed in detail here. See matrix exponential, and remember that quite many times they will ask you this also, that if unitary matrix is written in form of a Hermitian matrix, this is a favorite for TIFR. They are asking it again and again. And one of the concept again that is quite useful, that if matrix is diagonalizable, then you can write determinant of e ki power a is equal to e ki power of trace of a. So this as a concept, you see TIFR, NET and JEST all have asked this particular question. Okay. Now, one question I wanted to give you before I leave, and then tomorrow we'll meet with all the new questions. Okay, so in this category you have seen eigenvalues, eigenvectors. Again, one of the important concept that has been asked is this exploited concept, that is product of eigenvalues and the determinant of eigenvalues. So at times it is not necessary that you find each of the eigenvalues. So this is again theme number 2.3. So most often you're not required to find exact eigenvalues, okay, and you can do a little bit of calculation, and from there itself you can find. So let's say one of the very favorite question is, let's say you have A, this is a 2 cross 2 matrix, and it has two eigenvalues, e की power iota pi by 5 and another eigenvalue is e की power iota pi by 6. It says what is the smallest value of n for which a की power n would be identity. For which a की power n is identity. So what all you need to do is just take a determinant on both sides. Okay, just take a determinant on both sides. Always remember, if lambda 2, lambda 1 and lambda 2 are the eigenvalues of a, and let's say lambda 1 is not equal to 0 and lambda 2 is not equal to 0, if I want to find the eigenvalue of a inverse, it would be 1 upon lambda 1 and 1 upon lambda 2. Similarly, if I say that what would be the eigenvalue of power n, it would be lambda 1 raised to power n and lambda 2 raised to power n. So if I take a determinant of e की power n, it will be product of eigenvalues. It would be simply product of eigenvalues, and which is equal to determinant of identity, which is equal to 1. So I'll get e की power of iota n, and then this is pi upon 5 plus pi upon 6 equals to 1. So what I'll get, e की power iota n, and then 11 pi upon 30 is equals to 1. So think about this. What is e की power iota 2n pi? Only e की power iota 2n pi can be 1. Remember, e की power iota 2n pi can be 1. So it implies what? It implies that whatever comes in numerator, it should be what? It should be even multiple. So if I take n is equal to 30, if I take n is equal to 30, it is not going to give me an even multiple, because if I take n is equal to 30, then 30 cancels 30 and we'll have e की power iota 11 pi. E की power iota 11 pi would be minus 1. Okay, that would be odd multiple. Is that clear or not clear? I hope it is clear to you. So I will have to use something that gives me an even multiple above. So clearly I'll take even multiple here n. So even multiple, smallest even multiple would be 60. So therefore the minimum value of n would be 60 here. Okay, so all these concepts they're asking time and again. Another question I can give you. That particular question says that so it says that another question that was asked in JEST, and it is about this. So they have given that a is equals to a 30, 320 and 001, and they said that two eigenvalues they've already given. What is the third eigenvalue? What is the third eigenvalue? So let us first find what is this a. So remember, they have given to you. Let us first find this a, right? Because this a is unknown in this particular scenario, right? This particular a is an unknown quantity. So let us first find what would be a. So let us first find what is the determinant of a. So let us say that the third eigenvalue, let's say it is lambda. And if I find the determinant, it will be equals to 2a and this is minus 9. So determinant will be 2a minus 9. So this particular determinant of a would be equals to product of eigenvalues. So I'll write 2a minus 9 will be equals to minus lambda. Okay, another thing that you can use from here is this. I know that a plus 2 plus 1 would be simply lambda, right? A plus 2 plus 1 would be simply lambda plus minus 1 plus 1. So these two will be cancelled. Sum of the eigenvalues, lambda would remain, and sum of the eigenvalues is equal to trace. Remember. So sum of the eigenvalues is equal to trace, and trace is equal to what? A plus 2 plus, so lambda would be equals to a plus 3. So if I use here, what I'll get, minus a minus 3 will be equals to 2a minus 9. So this will be 3a plus, like there if we go, so a would be equal to what? Simply 2. And if a is 2, then the other eigenvalue would be 5. That you can do it on your own. 4 minus 9 is minus 5, so lambda would be 5. So please remember all these concepts I'm going to discuss tomorrow also. So tomorrow would be the last class. We have to pay focus on what I have told, only themes which are recurrent, which are being asked time and again. So I have just done a little bit of survey. Sorry for not having written all these questions. Like I could have taken a snapshot, but because of the lack of the time, I don't get that particular time. So I hope everybody is getting the point. Please remember, I have started the lecture with linear transformation. Then I have taken the route to the eigenvalues, eigenvectors. A few questions I have done, a few questions I'll do tomorrow. But remember these themes, try to revise these concepts, and I'll meet you tomorrow.